finishing out our study of enumerative combinatorics, we'll begin this lesson by learning about integer lattices in the set of integer pairs and paths in that lattice. So we're going to be living in the two-dimensional plane, and we're going to be drawing paths. However, these paths can only begin and end at points whose coordinates are pairs of integers. So here we have our standard two axes, our x-axis horizontal, our y-axis vertical, and I've drawn integer points. So for example, here is the point 0, 0, 0, 1, 0, 2, 1, 0, 1, 1, 1, 2, and so forth. So these points represent all possible x, y, where both numbers are integers. A lattice path is a sequence of edges connecting points in this integer lattice. You begin at one node, one integer pair point, and move to adjacent ones. You can only go up, down, or left, right a single unit at a time. So for example, this area is not an allowable lattice path because it does not actually connect points in our grid. This is also not okay. This is a path that does several steps at once. We are only allowed to go up, down a single step at a time, or left, right. So this is fine. This path starts here, goes up one, goes right one, and goes down one. So these are the sort of paths we're considering, a sequence of steps. And the steps have to either be up one, down one, left one, or right one. And if we start at a point in this grid and we do a bunch of these maneuvers, we'll always remain at points in this grid. An increasing lattice path is a special type of lattice path. It can only go up or right. It is not allowed to move down or left. In other words, because I can only go right but not left, the x-coordinate can only increase. It never decreases. And because I can only go up and not down, the y-coordinate similarly can only increase. It never decreases. Also, we're going to standardize paths so that they always begin at the origin, 0, 0. So this is no longer an allowable increasing lattice path. While this is a lattice path, it's not increasing because this arrow goes down. This green one, however, is an allowable increasing lattice path. It starts at 0, 0, and it only consists of moving right and up. So what are Catalan numbers? Well, the number of increasing lattice paths, remember that begins at 0, 0 and can only move right and up. And it has to begin at 0, 0 and will end at n, n, so it must end now at a point whose x and y coordinates are equal. But also along the way, it cannot contain any point j, k where k is larger. So the y coordinate is never allowed to be bigger than the x. The number of ways to connect 0, 0 to nn with an increasing lattice path and never having a y coordinate larger than an x coordinate is called a Catalan number, c sub n. So for example, if I want to compute c sub 1, we want to find all possible increasing lattice paths from 0, 0 to 1, 1. This path here is not allowed. Okay? It starts at 0, 0 and ends at 1, 1, and it only moves up and right. However, this point here is 0, 1, because we started by moving up 1. This is a point where the y-coordinate, 1, is larger than the x-coordinate, 0. And in computing Catalan numbers, we are forbidding such paths. This path, however, is fine. It moves to the right and then up. So it starts at 0, 0 and it ends at 1, 1. And also, the y-coordinate is never bigger than the x-coordinate. So another way of viewing this is you are trying to start at 0, 0 and end at an n, n. So here's 1, 1, or 2, 2, or 3, 3, and so forth. So you're going to end at some point on this line. But also, you never want to go above it. Above this line is where y is larger than x. So you need to take an increasing lattice path from the origin, 0, 0, to some n, n, while always remaining below or along this line. So to get to 1, 1, the only two possible increasing lattice paths would be to go up and over, or over and up. But as this picture here shows, if I were to go up and over, I'd be above the red line, and that's forbidden. So the only way to get from 0, 0 to 1, 1 with an increasing lattice path that never goes above this red line is to go right and then up. Now, if I wanted to go to 2, 2, I could go right, up, I could also go right, right, up, up. However, I can't begin with an up because then I'd be above the red line. And if I go right and up, then I can't go up because then I'd be above the red line. So there's only two increasing lattice paths that remain below this red line connecting 0, 0 to 2, 2. Either go right, up, or right, right, up. So C sub 2 is 2. This argument here shows that C sub 1 is 1. This is the only increasing lattice path from 0, 0 to 1, 1 that remains below the diagonal. Here's an image that I just pulled from Wikipedia to illustrate that C sub 4 is 14. Here are the only 14 possible increasing lattice paths that remain below the diagonal connecting 0, 0, which is the bottom left, to 4, 4. You can just go all the way over, then all the way up. You can do 3, and then 1, and then 1, and then 3. 3, 2, 1, 2. 2, 1, 2, 3, and so forth. These are the only 14 ways to go from 0, 0 to 1, 1, never going above the diagonal and only taking steps to the right and steps up. Here are some formulas about Catalan numbers that we're not going to derive. Okay, there is a nice recursive formula. C sub 0 is 1. There is a single lattice path that goes from 0, 0 to 0, 0, and that's just to do nothing, so there's one way to do that. But there's this recursive formula to derive C sub n plus 1. It's the sum, as I goes from 0 to n, of the product C sub I and C sub n minus I. As a hint for where this formula comes from, but again, we're not going to do the full derivation, I can be thought of as standing in for the first index I comma I, where your lattice path touches the diagonal. And then you try to count how many paths there are whose first intersection with the diagonal is at the point I comma I. If you sum all of those up, you can find that each one of those i's gives this product, sum them up, and you get C sub n plus 1. Alternately, there is an explicit formula, not a recursive one. And it's given as follows. The nth Catalan number is 1 over n times the binomial coefficient 2n choose n. The binomial coefficient can be seen as stating, if I'm going from 0, 0 to nn, I need to take n steps to the right and n steps up. There are 2n steps to take. You lay these out in a row, your 2n steps. Maybe it's right, up, etc. I have 2n things in a row, and each of them are either an up or a right. So for each of the 2n things, choose which n of them are, for example, going to the right versus going up. So 2n choose n can actually be seen to be the number of possible increasing paths that go from 0, 0 to nn. Because if all you do out of 2n spots is choose which n of them go to the right, and the rest therefore must go up, you'll have all possible ways of getting from 0, 0 to nn, but you haven't accounted for the need to only stay below this diagonal, and somehow that's what this fraction accomplishes. Okay, as I stated, we're not going to go through the derivation, but there is a recursive formula here, and also a nice explicit formula here. You can also show, by the way, that if the CNs are given by this formula, then it must obey this recursive formula. Conversely, if it obeys this recursive formula, then it will obey this here. So you only need to prove one of these, and then you can use that to derive the other one. An application of Catalan numbers comes in something called the ballot problem. Suppose there's an equal number of votes for candidate A and for candidate B. So candidate A has received n votes, and candidate B has received exactly n votes. The votes are then read out one by one. So someone stands there, pulls out a vote, and says A or B. And we know in advance there's going to be exactly n votes for each one. How many ways can the votes be read? Of those, how many ways can the votes be read so that the candidate who gets the first vote never falls behind? So when you reach your hand into the box, someone has to pull out a vote. And it's either going to say candidate A or it's going to say candidate B. Once you pull out the first vote, suppose for the sake of argument, it's candidate A. Of all the possible ways that could be listed out for the votes, how many of them, if you keep track along the way, will never have candidate A fall behind candidate B because candidate A got the first one? Well, the number of ways to read out the votes is 2n choose n. Of the 2n votes, simply choose the n locations for the votes for candidate A. The other positions are therefore for candidate B. So 2n choose n will be the number of distinct readings of the vote tally you could possibly have. But the number of ways for the leading candidate to never change is exactly the nth Catalan number. As the votes are read, you can imagine one candidate means move to the right and the other candidate means move up. They do get an equal number of votes, so if we begin at 0, 0, we're going to have the same number of moves right as moves up, so we're going to end up at n, n. And if we declare that whichever candidate gets the first vote must be moved to the right, and the other candidate therefore means move up, if we declare this candidate is never falling behind the other, then moving to the right, in other words, the x-coordinate, is never less than the y-coordinate or moving up. So we never have the y-coordinate larger than the x-coordinate. In other words, we never go above the line y equals x. And that's exactly what Catalan numbers counted, the number of increasing lattice paths that go from 0, 0 to n without ever crossing the line y equals x. So the Catalan numbers actually tell us how many ways we can read out the ballots, assuming both candidates got an equal number, so that the person who receives the first vote is never behind. One interesting thing to point out is that this binomial coefficient tells me all of the possible ways to read out the votes. The Catalan number was 1 over n plus 1 times this. So of all the possible ways, 1 over n plus 1 of them has the property that the starting candidate never falls behind. As n gets larger, 1 over n plus 1 gets smaller. So as n gets larger and larger, it becomes more and more likely that who is ahead will change as you count votes. This is, of course, assuming that the two candidates got an exactly equal number of votes to begin with. Let's move on with a study of what are called Dyck words. How many ways can I take n pairs of parentheses and list them out in a correctly matched way? And what do I mean by this? What I mean is you're not allowed to close a parenthesis before it was opened. So for example, if we have 3 pairs of parentheses we need to put down, these are all valid. Open, close, open, close, open, close. Open, open, close, open, close, close. Notice that this parenthesis is proper, this one is proper, and then the outer one is proper. Here I have one proper parenthesis enclosed in another, enclosed in another, which I can read out as open, 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 close, close, close. Here I open and then close, then open, open, close, close. Again, the parentheses are all matched up properly. There are other ways to do 3 sets of parentheses. These were just for an example. But this would be an invalid way of putting down 3 sets of parentheses. I open and then close, so these 2 are now taken care of, but now I'm closing a parenthesis that hasn't been opened beforehand. So this way of listing out 3 open and 3 closed parentheses is not valid. If you think about it, this is basically the same problem as before about counting lattice paths. We have equal pairings of objects. An open parenthesis and a closed parenthesis, for example, could be votes for different candidates. And what we're saying is the number of open parentheses seen must always be at least as large as the number of closed parentheses seen. If the first vote is an open parenthesis, which it has to be, we require the number of opens to never be less than the number of closed. So this is actually the same as the ballot counting problem, and therefore the same as Catalan numbers. So the number of ways to write n pairs of parentheses in this syntactically valid way is exactly the nth Catalan number. And there's so much more to enumerative combinatorics. This last section, we're not especially saying the Catalan numbers are the most amazing thing in combinatorics and we saved it for last. Rather, we're just sort of saying that depending on exactly what it is you need to count and subject to exactly what constraints, different sequences of numbers pop up. Some have nice explicit formulas. The Catalan numbers has this really nice formula. The nth Catalan number is 1 over n plus 1 times the binomial coefficient 2n choose n. But other really reasonable things to define do not have explicit formulas, at least not known as of yet, like the partition numbers. How many ways can I write the integer n as a sum of positive integers? We don't have an explicit formula. At best, we can compute the values as we need them, just by laboriously computing them out. But different counting problems can yield interesting results and can be applied in many new scenarios. Depending on what you are studying, a new problem might arise and you might need to define an entirely new sequence of numbers. Here are some related questions that are studied in combinatorics. How many ways can I stack n blocks in various rows so that a short row is never placed under a long row? In other words, I'm stacking horizontal collections of blocks in a way that would like stand up as a structure. I'm not allowed to place something longer on top of something shorter. This is what are referred to as Young diagrams. This is something that is often studied in combinatorics. How many ways can n objects be arranged into k disjoint cycles? We didn't really discuss permutations and cycles, but arranging n objects into different cycles is what are used to define Stirling numbers of the first kind. How many ways can we arrange n points, connect them with edges, subjected to various restrictions and refinements? Maybe edges aren't allowed to cross, maybe 2 points can't be connected by more than one edge, etc. This is graph theory, which we will study in the next unit. And there's a whole bunch more that goes into combinatorics. This unit was certainly not meant to be an exhaustive study of combinatorics. It's a very large field with a lot of people doing a lot of different things.